Good morning. So yesterday, someone bumped into my camera, knocked it over, and broke the screen. So for the next couple weeks, there'll be screen recordings instead of the actual recordings that'll post. Matrix algebra last time, right? Oh no, we did square matrices last time, that's right. The types of matrices. Oh boy, today's the fun one.
On homework 2, it uses like something from the book, like a formula for to like use square matrix. Should we use that on the test if we get that?
Yes, that's fine.
Or can we do it the way we learned in class?
Either one. Unless it specifically says use the formula. But I doubt it will. Echelon form. Starting with row echelon form. Matrix is in row echelon form if the first non-zero entry in each non-zero row is 1. If row K does not consist entirely of zeros, the number of leading zero entries in row K plus 1 is greater than the number of leading zeros in row K. All right, this just means that there are no non-zero entries below a leading 1. And if there are rows whose entries are all 0, they are below the rows having non-zero entries. So all of your 0 rows occur at the bottom of your matrix. This is row echelon form. Right. So again, the first non-zero entry in each row is a 1. We call that a leading 1. Every entry below a leading 1 must be 0. And all of your 0 rows occur at the bottom. Then we'll be in row echelon form, or REF. Then we have what's called reduced row echelon form, or row reduced echelon form, RREF. So matrix is in reduced row echelon form, or row reduced, if it is already in echelon form. So all 3 conditions for REF are satisfied. And the first non-zero entry in each row is the only non-zero entry in its column. So in addition to everything below a leading 1 being 0, everything above it must also be 0. Watch the lecture video on this for proof. What's the proof? I don't think it's on this. There is a proof in that video, though, that gives you the method of row reducing.
What are these 2
We'll get there. That's for next time. But we'll be using this for solving systems. Elementary row operations. There are 3 of them. Type 1 is to interchange 2 rows. Type 2, multiply a row by a non-zero constant. Type 3, replace a row by the sum. Okay, learn how to spell. Replace a row by the sum of that row and a multiple of another row. Those are your 3 elementary row operations, which should look familiar, by the way. Those are the same 3 operations that are used on systems of linear equations to get an equivalent system. I wonder if that's a coincidence. Row equivalence. We say that a matrix A is row equivalent to a matrix B if we can obtain B by performing a finite sequence of elementary row operations on A. And we'll represent row equivalence with a tilde. And so that'll be read A is row equivalent to B. So you have 2 matrices, B and C, both in reduced row echelon form. If A is row equivalent to B and A is row equivalent to C, then B and C are the same. This says that the row reduced form of a matrix is unique. There's only one. Notice it doesn't say anything about row echelon form. That is not unique. Elementary matrices. Start with the identity matrix. Perform exactly one elementary row operation on it. your result is what's called an elementary matrix of the same type. If E is an elementary matrix, then E is non-singular, and its inverse is also an elementary matrix of the same type. With elementary matrices, we can redefine row equivalence. So a second definition of row equivalence. Matrix B is row equivalent to a matrix A if there exists a finite sequence, give me 1 minute, of elementary matrices E1, E2, Ek, such that B is Ek times Ek minus 1, yada, 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 times E2 times E1 times A. Right, so there's a sequence of elementary matrices where when you multiply them to A, you get B.
Can you go back? Please, May.
And don't forget, these will be posted at the end of class. Good. Elementary matrices not really used that much in terms of calculations. However, they are used in theory. Right. I believe the theorem in the slides that goes over the method is every matrix has, or every matrix is row equivalent to a row reduced matrix. And then the proof actually comes up with the method of row reducing. So I'll refer you to the video for that derivation. I'm just going to use the method. So we want to put this matrix into row echelon form. In other words, we want to find a matrix in row echelon form that is row equivalent to A. So here's the general algorithm. And this is going to require a lot of bookkeeping. Start with your matrix. Look for the first column that has a non-zero entry. That is your pivot column. In this case, column 1. Look for that first non-zero entry. That is called your pivot. If it is not 1, make it 1 by using type 1 row operation. There can be a slight adjustment to that. If you have a 1 in that column, you could also just interchange 2 rows. I'm sorry, type 1 is the interchanging 2 rows. You can just interchange the 2 rows to move the 1 up. Well, in this case, no need to do that. 1's already in that first spot. So I'm going to circle it. That is our pivot. We now use that pivot to zero out every entry below it by using type 3 row operation. Remember, type 3, you replace a row with the sum of that row and a multiple of another row. So look at the 2. How would you make that 0?
-2.
Multiply row 1 by -2, add it to row 2, and replace row 2. Right, so typically what you would do is you do this as the representation. For the sake of space, I don't write that second part. Right, I always just have it implied that whatever that second row is the one that's being replaced. Notice how I didn't write it. I didn't write it this way. That is not a row operation. Because I'm still working in the same column, I typically do both steps at once. Right? The algorithm is you zero out the first entry below it, then you look, is every entry 0? No. What's the next non-zero entry? You make that 0. I do all of that at once. Again, for the sake of space. So now I'm also going to look at the third row. That entry is a 3. How would you make 3 0? Subtract 3. -3, row 1 plus row 3, replace it with row 3. First column is easy, 1 0 0. First row is also easy. Right, because we're not touching the first row. -2 times 2 plus 4. -2 times -3 plus -2. What is it? -2 times -3 is what? 6. Plus -2. What was it?
Sorry.
4. Oh, this one's going to be really hard. Negative 2 times 0 plus 2.
So,
Oof. There's your new second row. You're starting to see how this process can be extremely tedious. Now just imagine you made an arithmetic error on one of those entries that now screws your entire process. Every matrix resulting from that now is wrong. Do the same thing for row 3. Negative 3 times 2 plus 6.
0.
Negative 3 times negative 3 plus negative 4. So negative 3 times 0 plus 3. Eliminate row 1, column 1, and look at the resulting matrix. You do the same process. I will get rid of these lines. This is the idea. Because you've already handled the first column, right? And obviously you're leaving the first row alone. Now you look at that resulting submatrix. Repeat the process. Look for the first column with a non-zero entry. That is your pivot column. Which column?
Technically.
Right. Second column of the submatrix, but column 3 for us. What is the first non-zero entry? Which is in what row? That is our pivot. Is it 1? Make it 1. So what I'm going to do is get rid of those lines. This process is also going to require a lot of space. How would you make 4 1? By using type 2, which is multiplying by a constant, non-zero constant.
1.
So I'm multiplying row 2 by a quarter. Now again, technically the notation is this. Row 2 is replaced with a quarter row 2. But again, it's always implied that with constant multiplication, it's replacing the same row. So I'll just leave it as a quarter row 2. Nothing's going to happen to the first column, right? Nothing's going to happen to the first row. Well, that second column is also nice because it's zeros. Now, every other entry in row 2, right, so row 3 also stays the same. Every entry in row 2 now gets multiplied by 1/4. You get 1 1/2. Oh, joy. We get to deal with fractions now. Nowhere did it say that your entries had to be integers. That is still our pivot. You now zero out every entry below it. There's only one entry below it. So what would I have to multiply 1 by so that when I add it to 5, you get 0? Negative 5. Second row is going to remain the same. We're not touching it. The only thing that's changing is row 3. But the first 2 columns of row 3 are zeros. Right? Because we had zeros above as well. So they're not going to change. We only have 2 entries we have to worry about. And one of them, we already know because we wanted to make it 0. We only have 1 entry to deal with. Negative 5 times a half plus 3.
1/2.
Yeah, 1/2. So you eliminate rows and columns. Right, so we were working before technically with a submatrix here. Right, so that's already been taken care of. We eliminate column 1 because that's all zeros anyway. We now eliminate column 2 and row 1. We're just left with that 1/2. It's a singular matrix. It's a 1 by 1 matrix, which is extremely easy. Clearly, that 1/2 is going to be the pivot. The only step is it 1? If it's not, make it 1. How would you make that 1?
2.
Multiply by 2. So that's the last step. And again, I need another slide. That algorithm guarantees you get a row echelon matrix. That is not the only way you can do it. However, until you really get the hang of it, it is recommended that is the process you use. And I'll write that as REF of A. And that's the process. It's always those same steps. Now for my comp sci people. Write a code to put an arbitrary matrix in REF form. See if you can do it. And so essentially write a code for that algorithm. And you can't cheat and use mathematic and use the built-in command already. And so see if you can actually do it. Same questions, just shown differently here. I'm just asking for REF of B, which is the same as saying put B into row echelon form. Which means the process is going to be the same. And again, notice that there was no restriction on the matrix for REF, right? It didn't have to be a square matrix. You can do this on any size matrix. Becomes really fun if it's like a 20 by 20 that you're asked to row reduce. And maybe I'm evil when I say you have to do it by hand.
When does this come in handy? Like later down the line?
Next class, we'll start to use it. So Tuesday, we'll immediately begin using it. So right now, the purpose of this class is just get the hang of it. Then we'll actually see it in action. So we're actually going to be using it a lot, to be honest. At this point, 95% of linear algebra is this. So if you have a test question, you REF it, you REF a matrix, you're on the right track.
They used this in the first homework. Like one of the examples that they used for how to solve the equation was using the row reduce.
Unfortunately, that is because the textbook does this before matrix algebra, which sucks. So you can use that example now. But that's why in class I tried to avoid it. I don't like that they introduced linear systems and all this row echelon form before actually introducing matrices. Doesn't seem to make much sense to me. It's like, oh, here's a linear system. Here's a matrix. Here's row reducing it. Okay, what's a matrix? We'll do that in chapter 2. Yeah, doesn't make sense to me. There's very few linear algebra textbooks that actually start with matrices. That's chapter 1. I hate it. So remember, start with your matrix. And I will say on the quiz and exam, I will specify in the problem when I want you to do it by hand versus using technology. I think there's a mixture in the quiz of having to show each step out and using a calculator to do it, just to interpret it. Step 1, look for the first column with a non-zero entry. What column is it? What is the first non-zero entry? In what row? So the 1, 1 entry is the pivot. Is it 1? You have to make it 1. But I'm going to alter this a little bit. Look in the pivot column. Is there a 1? So instead of making -4, 1, I'm just going to interchange those 2 rows. Which rows?
1, 2.
All right, so that's the notation for interchanging 2 rows. And I actually want to take a pause. Everything we've mentioned, right, with the row echelon form, the reduced row echelon form, elementary row operations, have equivalencies with columns. There are elementary column operations. There's column echelon form, reduced column echelon form. And they all have similar definitions. We do not look at those. If you take a more advanced linear algebra course, you may see them. So either graduate level, or obviously it won't be now, but an honors linear algebra course might go over the column stuff. I have no idea what that's useful for because I've never actually used it. But in math, it doesn't matter. Math, we don't care if it's useful or not. It's there, it's interesting, so we study it. And when they ask, what's it useful for, we just laugh. We go, who cares? It's interesting. In fact, generally, we're happy when it doesn't have an application. Person who came up with group theory, for instance, was really excited because, like, finally, a math that isn't going to be applied in physics. And then string theory came along, and it uses group theory, and he was extremely pissed off that his math had an application in physics. I'm just going to do this. I'm just going to paste it as a picture. I don't feel like constantly opening up my laptop. Good enough. Oh, yes, of course, now designer pops up. Go away. And I don't think I, yep, good, so I can't erase that now. And I won't keep circling the pivot. I only did it for the first one, just to make it stand out what we were doing. 0 out, now every entry below the leading one in column 1. Right, if you haven't noticed by now, it's always going to be the additive inverse of that entry times the row plus that row that you're replacing it with. Right, so additive inverse of -4 is 4, so I multiply row 1 by 4. Additive inverse of 6 is -6, that's what I'm multiplying by. So it does make it really easy. Not doing anything to row 1, it stays the same. Column 1, the whole point was to get zeros below the 1, so that's easy. Now we just have those 4 entries left to find. And this is just basic arithmetic, which is really hard. 4 times 2 plus 1. 4 times -5 minus 6. Said minus 6, technically plus -6, but same thing. Yeah. That already looks like it's going to be hideous. -6 times 2 plus 3. What is it?
What did you say again?
-6 times 2 plus 3. -9. Right, it's -12 plus 3. Oh, that's promising. I like that. -6 times -5 plus -4. That makes me very happy. This is where I'm going to, again, deviate a little bit from the algorithm. Because it doesn't make sense to make that 9 a 1 just yet, when I can just do row 2 plus row 3 to completely zero out row 3. And that avoids fractions. This is an elementary row operation, right? It's 1 times row 2 plus row 3. That is technically a multiple of row 2. Right, so these row operations are located in your calculator if you have the Inspire. I don't know if they're in the 89. They might be somewhere. But it has 4 operations in it. One of them is just the row add, which is essentially type 3. You can think of like type 3.b. Now I'll go ahead and multiply row 2 by 1/9. Notice it doesn't change anything if I would have done it first and then zeroed everything out below it. You still would have rounded up with that row of zeros. And there's your REF. Which, by the way, is not what I got in my notes because I actually did make that -4/1 in my notes instead of switching the rows. But it doesn't matter. REF is not unique. So what I have and what we have in here are both valid answers. The only difference is in my row 1, I have 1, -1/4, 3/2. The other 2 rows are the same. But remember, this is unique. Reduced row is unique. So no matter how you go about doing it, you will get the same matrix. Now, if we examine this again, just real quick, how many steps were there? There's 1, 2, 3, 4, 5. 5 steps. That is a minimum of 5 chances to make an error. Actually, more than that. Right? Because in steps, 2 and 3, you had to find 2 entries each. So right there, that was 4 chances to make an error, just in those 2 steps. And that is a small matrix. Again, just imagine you get larger size matrices. It does increase your chance. Well, again, I say bookkeeping is extremely important. Make sure you write out the step.
Could you possibly check like your work on the calculator?
With REF, not necessarily. Because if you type in the matrix in your calculator and hit REF, it may give you something different. Because REF is not unique. Right? And that doesn't mean that yours is wrong. With REF, yes, because it is unique. Like I said, the calculator, the TI Inspire CX, does have row operations built in. So what you could do is you actually could use those operations. in your calculator just to make sure you get the arithmetic right. But just show each step by hand as well. And that's typically how I do it for larger size matrices. I'll have the calculator do the raw operations for me, but I write out the steps. And that's just the arithmetic. And that is how I will check your answer too. Which is why I said make sure you write down your step. That way I know if it's an arithmetic error you made or if you just didn't know what you were doing.
So if we did it like this on the test versus if we did it like the way you did it by making -4 1, it'd still be fine.
Yep. As long as you used elementary operations and you did everything correctly. Now for RREF. The algorithm for reduced row echelon form, row reduction. Step 1, put the matrix in REF form. So first we have to do the row echelon algorithm. Then the quote-unquote new stuff begins. All right, so I think you can do nested algorithms when you write code, right? You can define an algorithm and then recall it in a new algorithm. So obviously that's how you would do it. I wouldn't rewrite. Right, so I already know the row echelon form algorithm, right? We start with the matrix, and this is a 3 by what? Oh boy, a 3 by 5. But really the only important thing is how many rows there are. 3 rows, so not too bad. Oh, that is sexy. 2 columns are identical. So again, I think instead of making that 2 a 1, because the entries below it are both even, hence multiples of 2, I'll zero them out first and then worry about making that leading to a 1. And they should be negatives, right? -2, -4. And look what happens to the second column too. First 2 columns are identical, so first 2 columns in your row equivalent matrix will also be identical. That's nice. Now we have to worry about everything else. -2 times -1 is 2 plus 1, 3. -2 times 6 plus 10. -2 times 4, -8 plus 13, 5. -4 times -1 plus -1. Oh, I love seeing that. -4 times 6 plus 26, 2. -4 times 4, -16, plus 23, 7, right?
you technically zero out everything before making?
That's actually what I'm going to do. I'm going to go ahead and just zero out column 3. And then I'll just make those leading entries 1 together in the final step, right, at the same time. Negative row 2 plus row 3. That becomes a 0. 2 plus 2 is 4. Negative 5 plus 7 is 2. And now I can just make all of those 1s at the exact same time in the exact same step. No, sorry, 1/4 row 3, looking at the wrong matrix. 1/3 row 2, 1/2 row 1. 1, 1, negative a half, 3, 2, 0, 0, 1, negative 2/3, 5/3, 0, 0, 0, 1, 1/2. Step 1 complete. That is REF now, right? Now, to put it into reduced row. So once you get into REF, now you kind of work backwards. Start with the last row. Look for the column that has the leading 1. Zero out everything above it. All right, so we're looking at that entry, and we're going to zero out the 2 entries above it. Notice what's going to happen when we do that. For this matrix, only those 2 entries are going to change, right? Because everything else is 0. If I say only those 2, these 2 become 0, right? You don't have to worry about calculating these. These are the only 2 that we're going to have to actually do any kind of arithmetic on right now. It's going to be, and again, I'll do it in quote unquote 1 step because it's the same column I'm working with. First, actually I wrote that the wrong way. Whatever. First, we'll do the 2/3 row 3 plus row 2. Then we'll do negative 3 row 3 plus row 1. It's only those last 2 entries we actually have to do any kind of arithmetic on. -3 times a half. -3 halves plus 2. 1/2, right? Two-thirds times a half. A third? Oh, this turned out to be not as bad as I was expecting. Third plus 5/3 is 2. Now move over to the next column that has a leading 1. Zero out every entry above it. And then you repeat that process until you've done that on the second on the second row, which will be right now for us. Half row 2 plus row 1 replaces row 1. Right, and again, because the entries before that leading 1 are 0, the entries above those in row 1 don't change. Oh, but also, if you now look, this is nice for us, the entry directly after that leading 1 is also a 0, which means that entry in row 1 is also going to not change. That's nice. And then obviously rows 2 and 3 remain unchanged. Again, we only have 2 entries we have to worry about. And actually only 1, right? Because that has to be 0. That's why we were doing it. So it's just 1 entry we have to find. Half times 2 plus a half. What was a half times 2? 1, yeah. So 3 halves, right?
Would this make a square matrix diagonal?
Hmm?
Would this make a square matrix diagonal?
No. Wait, maybe. Where's my square matrix? No. Remember, diagonal's going to have to be both upper and lower. However, it will make it upper triangular, right? If it's square. If it makes it diagonal, it's a specific diagonal matrix. Specifically the identity matrix. There's no other diagonal matrix that would be in the reduced row echelon form. And there is your reduced row echelon form, or the row reduced. That's row reduction. And again, that is unique. So you can put the original matrix into your calculator and do row reduction on it. Put RREF, the matrix, to check. It will give you the same matrix. The process itself, it's not hard, is it? All right, it's not a hard process. It's just tedious. That's what makes it hard, is the tediousness of it. Now imagine doing this process with variables. I wonder if we're going to have to do that. spoiler alert, yeah, we will. And what's even worse is a lot of the time you can't even use a calculator for it. We'll have to do it by hand. Will this take less than 12 minutes? I guess we'll find out. If not, it'll be left for you to finish. All right, so we have a matrix D and we want to row reduce it. What's the first thing we want to do?
Find a row echelon form.
Put it in row echelon form. -1 row 1 plus row 2, right? And then -2 row 1 plus row 3 would zero out the first column. And yes, again, by the way, this is where graph paper is very useful. Really helps keep everything nice and neat. -1 times -2 plus 1. -1 times 3 plus 4. -1 times 1 plus -1. -1 times 2 plus 3. We all agree that that should be the second row. -2 times -2 plus 5. Oh, no, I'm sorry. -2 times 3 plus 9. -2 times 1 plus -2. -2 times 2 plus 8. Ah, my notes are wrong. Excellent. Now they're completely useless. We agree that should be the third row. Good, now I've got confirmation. If I'm wrong, it's not my fault. What do we want to do next? And then do what?
Add -3 row 2, row 2.
Or you could do what?
Subtract.
There are two things you could do.
Multiply 3 and then subtract.
So that's what he was saying. -3 row 2 plus row 3. Which is, by the way, what I'm going to do. Or you could do what? If you're following the algorithm to the letter, you'd make that 3 a 1. You'd multiply row 2 by a third first. Yeah, I don't see the point in doing that just yet, so. Oh, yes. Negative 3 times 1 plus 3. Negative 3 times negative 2 plus negative 4. Negative 3 times 1 plus 4. Yeah, I think I will. With this step, I will do this. Multiply row 2 by a third and row 3 by a half. And so actually, before I move on, we all agree that's the new row 3. 0, 0, 0, 2, 1. Oops. Yeah, no, I'm doing a third. Yeah. Oh, look at all those fractions we get to work with. Isn't that just so exciting? We all agree up to this point? And all the arithmetic is correct? Excellent. Again, if it's not now, it's no longer my fault. Now what do we want to do? So we've got it into row echelon form. What's the goal now? How?
Starting with the first one. Looking at the
Yeah. Start with row 3, look for that leading one, and do what?
make everything above it correct.
All right. So now just make all the elements above leading 1 0. All right, that's the next goal, which will be done in 3 steps, but 2 written steps. Two-thirds row 3 plus row 2. Oh, yes. I love it when it's something simple like that. And then negative row 3 plus row 1. One, negative 2, 3. All right, so those should be the first 4 entries of row 1. First 4 entries of row 2. And then row 3 is unchanged. All right, so the only thing to do is find the entries for rows 1 and 2 in column 5. 2/3 times 1/2. Oh, yes. 1/3 plus a third. Oh, yes, that was easy. I like that. -1/2 plus 2. Now it's just one more thing to do, right? Two row 2 plus row 1.
Why would you do that?
Where's the leading one in row 2? Again, it's the leading you're interested in, nothing after it. One, -2. That entry will change. This entry won't change, right? Because there was a 0 below it, and then that entry will change, and everything else should be the same. Actually, I'm sorry. That becomes a 0 not. So 2 entries we have to find, columns 3 and 5. Two times 1/3 plus 3.
11/3.
2 times 2/3, 4/3, plus 3/2. Oh, joy. 4/3 and 3/2 would be what? 17/6 sounds right. Wow, somehow I got the right RREF here, though. I must have done something funky. Oh, I wonder if, yeah, I probably did something different to get a different REF. Okay, yeah, that's what I did. Good. Again, process itself, not really hard. It's just keeping track of all the steps. A lot of chances for mistakes. So the first homework was due already, so let's get rid of that. Don't forget, second homework is due Tuesday. Third homework will be due next week. And continue to look at the projects.